So first of all, indicator is a substance which shows some color. We don't know the chemistry behind it. Why does it shows color? So there must be some reason why it is showing color. In this solution it is showing pink, this solution it is showing colorless. Okay, so there are reasons for it. So first of all, we'll deal with one of our favorite indicator, that is phenolphthalein. Okay. So it is basically denoted by this one, HPH. So when it dissociates, it gives H plus pH minus. Now this HPH in undissociated condition is colorless. Okay. pH minus is pink. Okay. So when it dissociates, it shows pink color. When it doesn't dissociate, it shows no color, colorless. Now, if you want to find out the equilibrium constant, the expression will be like this: H plus pH minus H pH. Now, in this phenolphthalein solution, if I want to put some acid, okay, or I put a little bit of acid in the phenolphthalein solution, what happens? So when we put some acid, let's see, acid will give you what? H plus. So this phenolphthalein solution is already having H plus. Okay, so this phenolphthalein solution will give more pinkish color if this reaction proceeds in forward direction. Now when you put it in acidic solution, what happens? Acidic solution already has H plus. So it will give a effect which we have already studied, is called common ion effect to this forward reaction. Okay. So this common ion effect will cause what? This common ion effect will reduce dissociation of HPH. Hence, the reaction will tend to go in backward direction. As soon as the reaction goes in backward direction, HPH remains undissociated and hence it is colorless. Solution. So now I am adding a base. What will happen? Base will give OH minus. As soon as it gives OH minus, what happens? It takes away OH minus, consumes H plus to form water molecule. Okay? OH minus consumes H plus to form water molecule. So whenever this reaction is going in the forward direction, if the products are taken away, so as soon as this happens, this, what does this mean? Products are consumed, right? The product are consumed. As soon as the product consumes, what happens? Which reaction is favored? The forward reaction is favored. Forward reaction is favored. As soon as the products are consumed, means products are taken away, more and more HPH will dissociate. So dissociation of HPH, that is phenolphthalein, increases. So amount of pH minus increases and hence the color in the basic solution is pink. So we'll talk about methyl orange now. Methyl orange is denoted by MEOH. It dissociates like this: Me plus OH minus. Okay. So here let us see what happens if you add acid. So as soon as you add acid, it will give you H plus ions, which will consume OH minus ion. So product is consumed. If products are consumed, forward reaction will be favored. Is favored. So a lot of Me plus will produce. The Me plus color is red, and this is yellow. Okay. And in acidic solution, it shows orange or reddish color. When you give base will give you which minus ions, which will have an effect like common ion effect over here. So dissociation of MEOH decreases, hence concentration of MEOH increases and the color remains yellow. Henderson's equation for indicators. First of all, indicators have two forms. One is acidic form like this. So if you put it in water, it will dissociate. It will give H plus In minus. If this is the acid form, this is conjugate base form. Okay. If this is the acid form, this is conjugate base form. Now, if you want to find the dissociation constant for the indicator dissociation, then it should be In minus H plus by HIN. I'm not going to take the water, definitely. I think this is okay with you guys. Now, the concentration of H plus is what? KIN. This I will be in subscript. Okay? Into HIN concentration. Okay? Below that, it will be In minus. Okay? So, if you do log of both this, so you get log H plus. This will be log KIN plus log HIN by In minus. If you take negative in all the sides, so this will be pH, this will be pKIN, and this will be plus. I'll keep it plus, I'll just inverse this one. So log In minus by HIN. Okay. So base form by acid form, nothing else. So at equivalence point means at the point where it is reaching equivalence, definitely In minus, that is the base form, will be equal to HIN. Base form will be equal to acid form at the point of neutralization. At the point of neutralization, base form will be equal to acid form. This point is called equivalence point. Remember why indicators are used. Indicators are used to detect the point of neutralization during a titration of a base and acid, right? When a base and acid is titrated, indicator will be used as a to denote the point of neutralization, and that point is called equivalence point. Now this point will come when the base form of the indicator will be equal to the acidic form of indicator in terms of concentration. So if this two is equal, then this will be log 1. So at this point, pH will be equal to pKi. So this is an important relationship. So this is Henderson's equation for indicators. Okay, this one. देखो, phenolphthalein is not a suitable indicator for titration of weak base versus strong acid, because OH minus ions given by weak base is not enough, is not sufficient, right? Is not sufficient to shift the pH to 8.3, because phenolphthalein has a range of pH. Phenolphthalein generally acts from 8.3 to 10.5. This is the pH range of phenolphthalein. So here where it is acting, accordingly you have to calculate. Okay? So if you use weak base, the OH minus ions given is very less, and that is not sufficient to shift the pH to 8.3. Similarly, methyl orange is not a suitable indicator. Not a suitable indicator for titration of weak acid plus strong base. Why? Because H plus given by weak acid is not sufficient to shift the pH to methyl orange requires around 4.5, so 4.5 is not sufficient. Okay. First of all, we'll have 4 curves. In y-axis we have pH, and in x-axis we have milliliter of base added. Okay. We are talking about n by 10 acid versus n by 10 base. Okay. That is the standard taken for this curves. We are talking about an strong acid, strong base neutralization. It will go like this. First of all, this is pH. So pH is increasing as you put in base into acid, because acid will be in conical flask, base will be in burette. So as soon as you put this base into acids, the pH is increasing. After that, it takes a sharp change like this. Then again, it goes like this. This sharp change occurs between pH of 4 to 10. And that is why in this case, The indicator that can be used is both methyl orange or phenolphthalein. Both you can use. Okay, both will show the equivalence point because the range is so big. Next, pH, milliliter of base. pH, milliliter of base. Okay. So see, we are talking about weak acid and strong base now. So if it is weak acid, definitely the pH is not going to start from a very low point. Okay. So this started about say from 2, but this definitely won't start from 2 because it has a high pH. Weak acid has a high pH. After that, it increases, base is giving, then a sharp change again, and then this way. Here, this sharp change occurs in between generally 7 to 10. So in this case, the equivalence point is shown by HPH. Okay. So weak acid, strong base, phenolphthalein will be the indicator. Next, pH, milliliter of base. Okay. We'll talk about strong acid plus weak base. So when you're talking about strong acid, again it will start from the bottom, right? Bottom it will start. Have a small here like this. So this is normally in the range of 4 to 7. Okay? 4 to 7 is the range. And in 4 to 7, we know very well methyl orange works very well. No problems. Next one is pH, milliliter of base. We will talk about weak acid plus weak base. So unfortunately for weak acid and weak base, there is no sharp change. There is this kind of changes there. So no suitable indicator is there for weak acid and weak base. No suitable indicator is there. The range is approximately from 6.5 to 8.4. Sometimes we use phenol red. Okay. But actually for this kind of neutralization, it is very difficult to have an indicator. There is no indicator available at this moment. Okay. Now all this neutralization was base in budette and acid in your conical flask. Now let's see this one. Na2CO3 plus HCl. We know it very well when we talk about Na2CO3 and HCl, which is one of my favorite question in your tests. Okay, and J is also one of the favorite questions, Na2CO3 and HCl. So if you want to plot the same curve, okay, if you want to plot the same curve, suppose you have kept the base in the conical flask and you put HCl from the burette. So the pH is high at first because this Na2CO3 is basic, right? pH is high. What happens after that? It comes down like this. It comes down. As you add HCl, it comes down. Suddenly it shows a sharp change like this. So this is the first equivalence point. Na2CO3 becomes NaHCO3. Next, it again comes down like this. Again shows a sharp change. The second equivalent point. So this is equivalent point 1. This is equivalent point 2. Okay. So that is why Na2CO3 and HCl has two equivalent points. And we know it very well. One of them shows that is in between HPH and methyl orange. See, when the range is at the top position, that is pH is high. At high pH, which will show neutralization? HPH. So HPH always shows half neutralization. Now I think another mystery of your life is clear. And at this point, MEOH will act, right? So this shows full neutralization. Okay.